Welcome back to the deep dive. In a world, often feeling overwhelmed with information, especially around scaling tech, you've likely heard ZK rollups mentioned. A lot.
They get pitched as this silver bullet for making blockchains faster, cheaper.
Right. And then there's Kaspa with its really unique block DAG setup.
Yeah.
It makes you wonder, how do you even build new layers on that?
Exactly. It's a distinct challenge. Scaling meets this very different base layer. You can't just, copy-paste solutions. It needs something tailor-made.
So today, we're really diving deep into these technical papers you shared. It's like the blueprint, basically, for putting based ZK rollups onto Kaspa.
Yeah, we're going to try and unpack that whole interaction, the L1, the L2.
How they talk to each other.
Precisely. Our mission, pulling right from these sources, is mapping out those core ideas. How do the parts communicate? How do funds move securely? What's the flow of information, of value? It's all about understanding their technical vision.
And for you listening, why should you care? Well, this isn't just like abstract tech talk.
Not at all.
It's about understanding how future dApps, the things you might actually use for trading, gaming, whatever, could get way faster and cheaper by building on Kaspa's strengths.
Hopefully you'll see how these complex pieces potentially fit together. Maybe have them aha moments.
Okay, let's set the scene then. What exactly is a based ZK rollup? Keep it simple.
Okay, think of a ZK rollup as a kind of super efficient shortcut for the main blockchain, the L1.
Right.
It takes a whole bunch of transactions, processes them off the main chain, and then generates a special kind of proof, zero-knowledge proof, or ZKP.
Right.
This ZKP mathematically guarantees that all those off-chain transactions were done correctly. So the main chain, L1, doesn't have to redo all that work. It just needs to check the one proof.
Huge efficiency boost. Makes sense. So the heavy lifting is off-chain. L1 just verifies the summary proof. What does the based part mean?
Based means it ties its ordering directly to the base layer. The data for the L2 transactions, the payloads or blobs, they get committed to L1 in the exact sequence L1 receives and includes them.
And why is that important?
It's fundamental because L1 dictates the order. The L2 operator, the entity running the rollup, can't just reorder transactions for their benefit or censor things. L1 provides that undeniable sequence.
So L1 isn't running the L2 code, but it is the source of truth for the data order.
Yeah.
And it verifies the final proof. According to the research, what are the key things L1 must do?
Three main things, really. One, collect and aggregate that L2 transaction data within its blocks, giving it that L1 order.
Yeah.
Two, crucially, L1 needs the built-in ability to verify those ZK proofs submitted by the L2 operators.
Natively.
Natively, yes. And three, it needs mechanisms to handle the entry and exit of L1 funds, like KAS, moving between the layers.
Why is it so critical that L1 itself verifies the proof? Couldn't users just check it?
Well, they could, but L1 verification offers huge advantages. First, it lets you use native KAS directly on L2 as collateral, because L1 knows the state is valid. Second, it creates a single consensus-enforced point of truth for validity. No need for everyone to run their own verifier. And third, maybe the coolest part, it gives new L2 nodes a trustless way to sync up. They just check the latest verified state commitment on L1.
Right, that simplifies things. Now, building this on, say, Ethereum with smart contracts is one approach. Kaspa uses UTXOs and scripting. How does that change things?
It changes quite a bit. On a VM chain, you often have a central smart contract holding the rollup logic state verification. With Kaspa's model, you don't have that single point. The functionality has to be embedded more deeply into the base layer's script language and even the block structure itself.
A more embedded approach, like you said.
Exactly.
Okay, let's get into that embedding. What specific L1 changes are proposed? Architecture, scripting.
Okay, a really foundational one is adding a new field in the block headers. It's called ordered history Merkle root.
Ordered history Merkle root. And what does that do?
It basically acts like a running commitment to the entire ordered transaction history. Each block's header normally commits to its own transactions, right? This field goes further. It includes a hash pointing back to the ordered history Merkle root of its main chain parent block. Then it combines that historical root with the Merkle root of the transactions in its own merge set.
Ah, so it's recursive.
Exactly. It creates this chain of commitments. So any block header effectively anchors a verifiable snapshot of the full ordered transaction history up to that point, gives L2 a solid foundation to prove against.
Got it. A verifiable history anchor. Now, to make L2 proofs checkable on L1, you need new scripting tools, right? New opcodes.
Yes. The absolute core is a proposed opcode, opbzk verify. This is the magic function. It takes the public inputs of an L2 state change, the ZKP itself, and it mathematically confirms right there in an L1 script if the proof is valid.
And that might be built from smaller pieces you mentioned.
They suggest it might be decomposed into lower-level crypto primitives, yeah.
But optizk verify is the conceptual linchpin.
And how does optizk verify connect back to that history root field? Through another proposed opcode, op-chain block history root. This lets a script look up the ordered history Merkle root value from a specific past block on the main chain.
Okay, so the ZKP needs to prove a state transition happened based on history up to point X.
And this opcode lets the L1 script fetch the history root for point X to check against the proof's claim.
Makes sense. The research flags something interesting about op-chain block history root, calling it stateful. What does that mean for users?
Stateful means its success depends on the current L1 state. Is the block it's referencing still available, not pruned? Is it considered part of the main chain right now?
So a transaction could become invalid later, not because of a double spend, but just because the chain state changed.
Potentially, yes. If the reference block gets pruned or reorganized out, that could be confusing for users. They float ideas like maybe a maturity period for such transactions, like Coinbase outputs, or maybe off-chain tools to warn users about relying on potentially unstable history.
Definitely something to iron out. And to even build optizk verify, you need the underlying math tools in the script language, elliptic curve stuff.
Correct. For efficient ZK systems like Gras16 or Plonk, popular partly because their proofs are small, Kaspa script needs elliptic curve operations. They propose opcodes for modular ADD, MUL, scalar multiplication, and pairing checks.
And these aren't pulled out of thin air.
No, they're based on well-established, audited implementations from places like Zcash, Geth, Ethereum, EIPs, so a solid cryptographic foundation.
Okay, history anchor, proof verification, EC math.
Yeah.
What about hashing? The sources mentioned needing a hash function good for both L1 and ZK proofs.
Right, that's a tricky one. You need something fast on regular CPUs for L1 consensus, but also efficient to compute inside a ZK circuit, ZK-friendly.
And the candidates?
They look at things like Poseidon 2, which is designed for ZK circuits, versus standards like Blake 2s or Blake 3, which are CPU speed demons.
What's the trade-off there?
Blake is faster on CPUs generally, and field agnostic, but it's much slower inside the ZK proof. The papers say maybe 20 times slower. Poseidon 2 is way faster in the ZK circuit, but slower on a CPU and tied to the specific math field of the ZK system.
So you're optimizing for L1 speed or L2 proving speed?
Pretty much, or finding the sweet spot. It's noted as an area needing more benchmarks and research before a final choice. They also bring up sparse Merkle trees, SMTs.
Not just for proving things aren't there.
Right. Also potentially useful within consensus for managing changing data structures, like mapping L2 IDs to their latest history commitments efficiently.
Okay, L1 changes are clearer now. How does the actual L2 state get represented on L1, this state commitment UTXO idea?
Yeah, this is key. L1 doesn't store the whole L2 state, just a cryptographic commitment to it, and this commitment lives inside what looks like a normal Kaspa UTXO.
But it's special. PTS, she said.
Exactly. Pay to script hash. To spend it, you have to reveal the original script data, the pre-image, that hashes to the lock, and satisfy the script's conditions.
What's in that pre-image data? What does the L1 script need to see?
Several things. The hash of the L2's program code, PROG, the actual L2 state commitment, often a Merkle root of the L2 state, though L1 doesn't care about the internal structure. It also holds the specific L1 history Merkle root this L2 state is anchored to, and maybe some auxiliary data like a verification key.
And updating the state commitment on L1 happens via
a proof transaction. This is an L1 transaction that spends the current state commitment UTXO, the before state, and creates a new one, the after state.
And the proof is in there.
Yes. The signature data reveals the pre-images for both the input and output state UTXOs, and critically, it contains the ZKP proving the state transition was valid.
The bridge between states. The research had pseudocode for how L1 verifies this proof transaction. Can you walk through the logic?
Sure. Roughly, the L1 script first checks the pre-images provided actually match the hashes locking the input and output UTXOs. Basic check. Second, it verifies the L2 program hash, PROG, is identical in both the input and output pre-images. The L2 logic itself shouldn't change mid-update.
Makes sense. And the L1 history connection.
That's where op-chain block history root comes back. The script uses it to fetch the L1 history route, specified in the new state commitment's pre-image. It checks that this fetched route matches the one claimed in the pre-image, ensures the new state is anchored to a real L1 history point.
And then the final step, check the proof.
Exactly. It calls opsk verified. It feeds it the public inputs derived from the state commitments and history routes, commit in, commit out, shrin, route, the preaug hash, and the ZKP itself.
So if opsk verify returns true, what does that fundamentally tell L1?
It tells L1 that the L2 program, PROG, when executed starting from commit in and processing all the L1 ordered transactions between history points, shrin, and route, mathematically must result in the state commit out. L1 doesn't run the L2 code, but it trustlessly verifies the outcome via the ZKP. It enforces that the L2 state it tracks is a direct, valid result of the L1 ordered data.
Okay, this setup enables some really interesting possibilities. Let's talk composability. What's atomic synchronous composability? Sounds powerful.
It really is kind of the ideal for complex DeFi or dApps apps. It means a single L1 transaction can interact instantly with multiple different applications or rollups, logic zones, reading and writing state across them all at once.
All or nothing.
Exactly, atomically. Either the whole multi-step interaction succeeds or it all fails together. This is what fueled a lot of early Ethereum DeFi innovation, for instance.
And the alternative is async composability.
Yeah, that's interactions via messages, usually relayed through the base layer. There's delay, no atomicity guarantee. The final outcome isn't immediately certain, less seamless.
So why do these based rollups, putting data on L1, enable the good kind synchronous composability?
Because the essential data for all parts of a multi-zone interaction is ordered and available on L1. If a transaction hits rollup A, then rollup B, the data for both is sequenced by L1. The final state commitments verified on L1 reflect that sequence. You can define cross-zone conditions within the scope of the L1 proof transaction. The outcome is tied to the L1 sequence, not waiting for slow messages.
But the sources mention a potential dependency problem. If Zone B needs the result from Zone A within the same transaction, doesn't Zone B's proof need to know about Zone A's change? Isn't that like merging them back together?
It's a fair question. It seems like it could collapse the separation, but the research argues it doesn't have to for a few reasons.
Okay.
First, this tight dependency only exists when zones do interact synchronously. You can design things to minimize that.
Ugh.
Second, and this is key, executing code is way, way cheaper than proving it, orders of magnitude.
Ah.
So the prover for Zone B does need to execute the Zone A part to get its starting state right. But crucially, it doesn't need to generate or verify the proof for Zone A's part.
So the execution dependency is okay because proving is the bottleneck, and that stays separate.
That's the idea. Provers are permissionless, but they might be specialized, not just running on basic hardware. The design goal is just to minimize those necessary cross-zone synchronous calls.
This leads right into proof stitching. If one transaction hits multiple zones, each with its own prover, how do the proofs combine for L1?
Proof stitching is the proposed solution. It's pretty elegant. Provers for the different zones involved in one atomic transaction basically collaborate to build the final proof L1 needs. Each prover only generates the ZKP for the execution piece within their own zone.
And these pieces are called sub-transactions.
Yeah, like distinct function calls or execution segments within one zone's logic, but all part of the bigger user transaction.
The sources describe the format for these pieces, a zero-knowledge proof message.
Right. It's a package deal. It contains an index number showing its place in the overall sequence, the inputs for that segment, like starting state, call stack, the outputs, resulting state, call stack, and pi the ZKP, just for that segment's execution.
And these individual proofs are conditional? What does that mean?
It means the proof pi itself is valid for its segment, assuming the inputs it was given, but its relevance to the whole transaction and L1 settlement depends on it being correctly linked or stitched with the proofs for the segments before and after it.
How does a prover get the right inputs if they depend on what another prover did just before?
They could coordinate off-chain, maybe, pass results around, or perhaps simpler, a prover needing the output from step N1 can just execute step N1 or the whole chain up to it themselves. Since execution is cheap, they can derive the correct starting state that way.
And the stitching process ties it all together on L1.
Conceptually, yes. L1 receives these proof messages. The stitching logic links them sequentially, verifying that the outputs of message n match the inputs of message n+1 following the indices until the whole chain is validated or fails.
Okay, let's connect this back for you, the listener. This stitching idea is how a potentially complex action, like maybe swapping token X on rollup A, which then triggers buying token Y on rollup B, could feel instant and atomic to you.
Right. L1 orders the data quickly. The different provers do their piece of the heavy lifting. Stitching combines combines it for L1 verification. You get atomicity without one giant slow proof.
Distributes the work, keeps it coherent.
Exactly.
Let's switch to managing funds. The canonical bridge, what's the goal there?
Simple goal. Let native L1 KAS flow into an L2 and be used there, typically as BKAS or bridged KAS, with a strict 1.1 backing. The L2 effectively gets custody of a pool of KAS UTXOs sitting on L1.
And there's entry into L2 and exit back to L1. How does entry work, putting KAS into the L2?
For an entry, you just send KAS to a specific L2 designated address on L1. The key point from the research is this gets validated inline by L1. The L1 transaction itself is the event. Meaning the funds can become usable on the L2 almost as soon as that L1 transaction confirms, even before a ZKP covering that specific deposit arrives. The L2 just observes the L1 inclusion and updates its state.
Fast user experience for deposits. What about getting funds out? And exit.
Exit is the other way around. You want your BKAS on L2 turned back into KAS on L1. This needs L2 state authorization first. And unlike entry, it's not instant on L1 inclusion. It requires the L2 operator to bundle this exit request and submit a ZKP proving it's valid according to L2 rules. L1 only releases the KAS from the bridge pool after verifying that ZKP.
So exits wait for the L1 proof verification. Entries happen on L1 TX confirmation. They mentioned an outbox for exit.
Yeah, it's like a queue on the L2. Exit requests, maybe other async messages too, go into this outbox. The prover's job includes proving the contents of the outbox in their next ZKP submission, delivering those results back to L1.
Okay, practical issue with entry addresses. That main state commitment UTXO, the one holding the L2 state hash, it changes constantly with every proof. You can't tell users send funds to this address if the address keeps changing, right?
Exactly. It's too dynamic. The proposed solution is static delegation P2S addresses. These are fixed L1 addresses that don't change.
Okay, how do they work?
Their script logic is different. Instead of needing their own proof, they delegate spending authority. The script basically says, the KAS sent here can be spent if the transaction doing the spending is also spending a main state commitment UTXO, and that state commitment UTXO is being verified by a legitimate L2 proof script right now.
So the static address piggybacks on the main L2 state verification.
That's a good way to put it. The delegation script checks if the transaction trying to spend its funds is also spending a state commitment UTXO. Then it checks if that state commitment script has the right identifying features, specifically the correct Perot cache and canon script hash embedded within its preimage.
Clever. But the research flagged an attack vector. What's the risk?
The risk is forgery. Someone could create a fake UTXO that looks like a state commitment UTXO. It has the right prog and canon hashes in its script preimage, maybe, but it's not part of the real L2 chain. Maybe it has fake state or history.
And a user sends funds to a delegation address.
And the attacker tricks the delegation script into pointing those funds towards their forged state commitment UTXO because it superficially matches the prog canon check. The funds get locked in a fake chain L1 doesn't recognize. L1 can't easily stop you sending coins to an address.
Ouch. How do they propose preventing that?
By using key-based state commitment UTXO authentication, every UTXO has a unique fingerprint, right? Derived from the transaction that created it.
Yeah.
They propose using this fingerprint to authenticate the chain of state commitments. The idea is to hard-code a specific Genesis UTXO fingerprint and the hash of the correct canon script directly into the L2 prog code itself.
So the L2 program knows its own authorized starting point and structure.
Exactly. When a proof transaction tries to spend a state commitment UTXO, the prog logic, which is enforced by upsk verify on L1, checks the fingerprint of that input UTXO. It must verify that this UTXO either came directly from the hard-coded Genesis fingerprint,
The very first one.
right, or that it came from a previous state commitment UTXO that also passed this check, tracing a chain of custody back using private witnesses like transaction details, ensuring it belongs to the legitimate chain started by Genesis.
What happens if someone tries to spend a forged UTXO? It might have the right prog canon hashes.
But its UTXO fingerprint won't trace back to the authentic Genesis via a valid chain. So the prog's internal check will fail when opsd verify runs on L1. The forged UTXO becomes unspendable by the legitimate L2 logic.
And this protects the delegation scripts too.
Yes, because the delegation script checks that the primary state commitment input is well-formed. Part of being well-formed is passing this prog check. So, the delegation script won't authorize spending towards a forged, unspendable state UTXO.
Okay, step by step, how does a new L2 actually get started using this?
It's fairly straightforward. The L2 team sends some KAS to a regular L1 address they control that UTXO becomes the designated genesis. They take its unique fingerprint and the hash of their compiled canon script and hardcode those into their L2 program, PROG.
Compile the props.
Compile the prog. Then, using the Genesis fingerprint, canon hash, prog hash, and whatever the initial L2 state is, they constrict the script for the very first real state commitment UTXO. Finally, they create an L1 transaction sending funds from the Genesis UTXO to this newly created state commitment script address. Once that confirms on L1, the L2 is officially live and anchored.
And this key-based chain authentication must make it much easier for new L2 nodes to sync up trustlessly.
Absolutely. A new node doesn't need to trust some third party for the state. They find the latest verified state commitment UTXO on L1, verify the fingerprints and prog canon checks for a few recent transactions leading to it, and they know they're syncing to the authentic chain derived from the known genesis.
Let's jump back to exits quickly. You said they're proof outputs. How does L1 make sure the actual KAS goes to the right withdrawal addresses when the ZKP is verified?
Okay, this is neat. The proposed L1 canon script, the one locking the main state commitment, does something specific. It calculates a cumulative hash of all the output UTXOs in the proof transaction, except for the one creating the new state commitment UTXO.
So a hash of just the withdrawal outputs.
Essentially, yes. This hash becomes a public input to the OP6K verify check on L1. Meanwhile, the L2 PRG, as part of its execution, calculates the same kind of cumulative hash over the withdrawal addresses and amounts sitting in its outbox that are meant to be processed in this batch.
And OP6K verify checks, they match.
Exactly. If the hash L1 computes from the actual transaction outputs doesn't match the hash the L2 PRG claims and proved via the ZKP, the whole proof transaction fails. It ties the ZKP validity directly to the correct L1 fund disbursements.
Very clever.
Yeah.
But what if there are thousands of exits? That L1 proof transaction could have thousands of outputs. Doesn't that hit block size limits, the end-to-const problem?
Yep, that's the challenge. If every exit needs a unique L1 output, you hit limits fast. They propose a couple of ways around it.
Like what?
One idea is using special P2-ish addresses on L1 that represent a group of withdrawal keys. The exit funds for many users go to this single address. Then individual users can claim their share later using something like a Merkle proof showing their key belongs to that group. Might need new opcodes for that, like KP10 introspection.
Okay, aggregate withdrawals. What's the other idea?
Make the L2 outbox part of the L2 state itself more formally. The L2 PRG could enforce rules like, you can't advance the main L2 state unless the outbox is empty, or maybe you can only process X withdrawals per batch if there's congestion. This way, the clearing of the outbox is part of the state transition being proved. They mentioned KAP10 opcodes, optx inputs SEK. It would be really useful here too.
All right, let's shift to the rhythm, throughput, fees, time.
Yeah.
How do you control how much load an L2 puts on the system, especially the provers doing that heavy ZK work?
Yeah, you need some kind of cap on the L2 computational load, which they talk about in terms of gas units.
Kaspa currently uses mass for block limits, mainly storage and L1 compute. The research says just using mass for L2 gas isn't efficient.
Right, because L1 script execution and L2 ZK proving are very different kinds of work with different costs. Lumping them under one mass limit isn't ideal. The proposal is for a two-dimensional throughput restriction.
2 dimensions.
Yeah. Miners choosing transactions would need to satisfy both a mass limit, like today, and a new gas limit per block. It makes block building a bit more complex, like a 2D knapsack problem.
Sounds tricky for miners. Any simpler alternatives mentioned?
They touch on maybe using something like Ethereum's EIP 1529, but for the gas dimension, that could create an in-protocol price for gas, making miner selection easier, just maximize fee per gas. It could also potentially direct those base gas fees to the provers.
What about per L2 limits versus one global gas limit?
Per L2 limits would be most economically efficient, but leads to an n-dimensional knapsack problem, which is even harder. So, for simplicity, they lean towards a single block-wide gas limit, even if it's a bit suboptimal economically.
And how do the provers actually get paid for burning all that gas?
The L2s themselves would add fees onto their transactions. The papers encourage these fees to be in KAS, which helps align incentives across the whole ecosystem.
Okay, now for a really core tension, the sources highlight, specific to Kaspa, the conflict between its parallel DAG structure and this idea of inclusion time proving.
Yeah, this gets right to Kaspa's design philosophy. The DAG and fast blocks mean transactions get included super quickly, often before their final canonical global order is fully locked in. There's execution uncertainty at inclusion time.
You don't know the exact state it runs against until a bit later.
Right. But true inclusion time proving, getting that L1 verified result, the instant data hits L1 ideally needs a perfectly known stable state at the moment of inclusion.
So Kaspa's speed and parallelism conflict with that ideal of instant L1 finality for L2 effects.
Fundamentally, yes. The source is presented as an unavoidable trade-off. And the design choice discussed is to keep Kaspa's core strengths, the speed, the parallelism, the resulting MEV resistance properties.
So what's the consequence of embracing that uncertainty for L2s?
It means that L2 state updates, fund releases from the bridge, anything needing L1 proof verification cannot be finalized on L1 the instant the L2 data arrives. The proofs have to be deferred. They wait until the L1 ordering settles and provides that stable history anchor point we discussed.
That raises a big question. What if the proof never shows up after the data is included? The proof availability requirement.
That's the critical thing to solve. The proposed model is time-bound proof settlement.
Okay, how does that work?
The L2 transaction data hits L1, gets ordered, achieves data availability, everyone knows it's there, but the L1 settlement of its effects, updating the state UTXO, releasing exit funds, is conditional. The required ZKP must be submitted and verified on L1 within a set time window, say P seconds after the data's L1 sequence is stable.
A proof deadline. What if the prover misses the deadline?
If the proof for a segment isn't validly submitted within time t, then that segment and potentially the whole atomic transaction it belongs to simply fails to settle on L1. It's like it never fully happened from L1's perspective, and there'd likely be penalties for the prover.
What's the main benefit of this time-bound model for someone actually using the L2?
It allows for really fast, user-side optimistic confirmation. Since the data is on L1 and ordered, its outcome according to the L2 rules is basically determined. A prover failing to prove valid included data would kill the L2's liveness, a huge incentive for them to submit proofs.
So users can trust the incentives.
Largely, yes. If you're running software that follows the L2 logic, you see your transaction data hit L1, you can compute the expected outcome, and you can optimistically confirm it on the L2 side almost instantly, trusting the proof will arrive for L1 settlement later.
I get L2 speed, trusting the system, while L1 confirms the global state change on its own schedule.
Exactly. The final L1 settlement latency is L1 sequencing time plus the L2 proving time. But as ZK tech gets faster, aiming for under 12 seconds, maybe near real time, that proving delay shrinks. It also avoids bloating L1 transactions with constant witness data overhead.
Were there discussions around refining this timeout mechanism?
Yeah, points were raised about maybe having default timeouts, but letting L2s request longer ones for complex stuff. How to isolate failures so one delayed proof doesn't mess up unrelated parts of a transaction. And linking prover reputation or fees to their reliability. But the key is, the final success failure state must be globally known and verifiable.
Let's loop back to that ordered history Merkle route. You mentioned the first simple idea was just hashing all transactions together. Sources revisited this, pointing out an inefficiency for L2s, or subnets as they call them here.
Right. The simple approach, hashing all L1 transactions into one history route, forces an L2 prover to process every single transaction between proof points, even unrelated ones.
Lots of noise.
A huge amount of noise, yeah. Makes proving inefficient.
So the fix is to somehow track history per L2.
That's the core idea. They propose structuring the main SQC field, that history route, as a route over individual commitments per subnet, called SQCI. Each L2 gets a subnetted.
How is the SQCI for subnet I calculated in a block B?
If block B has no transactions for subnet I, then SQCI-B is just the same as the commitment from its parent block, SQCI-BSP. If B does have transactions for subnet I, the new SQCI-B is a hash combining the old SQCI-BSP with those specific transactions for subnet I from block B in their L1 order. They also suggest including the global transaction index for cross-subnet context.
And the main SQC in the header is them.
A Merkle route over the SQCI-B values for all subnets considered active in that block.
What's the win for the prover?
Big win. Now, a prover for subnet only needs their own transactions as private input. To prove their SQCI was included in the main SQC route, they just need standard Merkle proofs, which are small logarithmic in the number of active subnets. Their input size drops dramatically. Proving becomes much more efficient.
But if subnets just keep getting added to that active set, doesn't it grow forever? That's the next problem, an unbounded active subnet registry. The solution proposed is pruning subnets.
How does that work?
A subnet is only considered active and included in the main SQC Merkle root if its most recent transaction occurred within a defined window, a finality depth based on DAA score, maybe like half a day. If a subnet is silent for longer than that, its SPSI gets pruned from the main active tree calculation. This keeps the size of that active set bounded.
So an L2 needs roughly one transaction every 12 hours or so to stay in the fast lane.
Seems like the implication, yeah. The SQCI structure itself would need to include the DAA score to enable this logic.
What if a subnet does go quiet and gets pruned? Can it still prove its history later? Yes, there's a fallback. They suggest maintaining another branch in the SQC structure, maybe one that doesn't prune or divide by subnet, tracking the total history. A pruned subnet could use this lower path if needed. It's also useful for apps that need all L1 transaction data, so the final proposed structure gets quite layered: hierarchical subnets, an expiry window F, global sequence numbers inside SQCI. The main SQC root combines commitments from recent blocks, maybe for KIPI6 style history proofs, plus the SQCI for all the non-expired subnets.
And pruned subnets can even prove they were inactive during a period.
Apparently so, yes. By showing a non-inclusion proof against the active STC root for that period, maybe once per expiry window F. And SMTs come back here as a way to efficiently manage that changing map of active subnet IDs to their SQCI commitments inside consensus.
Okay, last piece. The sources briefly mentioned standardizing the idea of a covenant. What does that mean here?
It builds on those special UTXOs, the state commitments, the delegation addresses. They have specific script structures, covenants. Many have static parts, like the core canon script, the prehash hash, and dynamic parts, the actual state commitment. The idea is to create a standard way to identify and hash just the static parts.
How would that work? A special marker?
Yeah, maybe a defined header or mask in the script that lets L1 isolate the static components. Hashing just those static parts plus the header would create a unique covenant identifier.
What's the benefit of having a standard identifier like that?
Two main use cases pop out. First, async message passing between L2s. A proof transaction from L2A, a covenant, could include a special payload marked system. L1 could verify that the sender ID in the payload matches the standard covenant identifier derived from L2A's script. Then L2B could trust messages from that verified ID, knowing they come from the audited logic of L2A. The second use case simplifies those delegation scripts for fund entry. Instead of checking prog and canon hashes explicitly, the delegate script could just check if the primary state commitment script being spent has the expected standardized covenant identifier. Cleaner, simpler.
Wow. Okay, we have definitely gone through a pretty intricate technical tapestry here. New opcodes, header fields, complex proof logic, data structures, all designed to enable these scalable atomic-based ZK rollups, specifically on Kaspa's DAG.
It's a very comprehensive vision, yeah. Tackling composability, state management, bridging funds, throughput, timing, leveraging Kaspa's uniqueness while designing around its specific challenges.
And clearly, it's ongoing research, ongoing design work, lots of interconnected pieces. So we've really seen how building these sophisticated L2s on a fast UTXO DAG like Kaspa, it's not just adding a layer. It demands deep changes, clever workarounds, balancing that raw speed with composability and the realities of consensus.
Definitely.
Now, thinking ahead, ZK tech itself is evolving incredibly fast. What other, maybe completely new cryptographic tools might pop up soon? Could they reshape these trade-offs again, maybe offer even more flexibility, or push what's possible on L1 even further?
That's the big question, isn't it?
Something to ponder until our next deep dive.